as per a request, I want to talk a little bit about the implicit differentiation problem. Suppose that you have some relationship between two variables, x and y. For example, x to the fourth plus y squared x squared equals y to the fourth minus 4x plus 1. By subtracting one side from another, you can always arrange it so that there's a constant on one side. So x to the fourth plus x squared y squared plus 4x minus y to the fourth is 1. You can always write an equation of this type as some expression involving x and y equals some constant number. Now, we have no idea typically what these graphs look like. They could fail the vertical line test in multiple places. The graph could cross itself. Many things could happen. But if you look at the pieces of the graph close to individual points, each one locally looks like the kind of y equals a function of x that we dealt with back in Calculus 1. We'd like to be able to calculate the slopes of these tangent lines where possible. Notice that I have to tell you both the x and y coordinates because my graph may fail the vertical line test, so telling you only x is not enough to tell you where you're at on the graph. So let's think about the explicit and implicit dependencies here. In the formula for f, which is again secretly a constant value, there are x's and y's. Locally, I'm thinking of y as being a function of x, so my dependency diagram starts with f at the top. At the explicit level, we have x's and y's, and we're thinking of y as being a function of x. Therefore, on the most basic level, everything is a function of x here. I want to think about the rate of change of function f as I change x, doing the diagram in the same way that we do for the chain rule. Firstly, the rate of change of f is 0 because f is a constant. Secondly, because of our dependency diagram, the rate of change of f with respect to x is the partial of f with respect to x plus partial of f with respect to y times dy dx by the chain rule. Both of these expressions represent the rate of change of f with respect to x, so they must be equal to each other. 0 must equal this quantity. So writing that fact down, 0 is partial of f with respect to x plus partial of f with respect to y times dy dx, which is what we're looking for. Subtract this term from both sides to obtain this, or using the subscript notation, we can write it this way. The slope of the tangent line is negative rate of change of f with respect to x over rate of change of f with respect to y. Now, you might be thinking that both of those are 0 because f is a constant, but we have layers to our thinking here. On the one hand, f will be defined explicitly in terms of x's and y's. At that level in the calculation, I'm thinking of the x and the y as independent variables, and only when I move to this layer of the picture do I take into account that I'm thinking of y as actually depending on x. So despite appearances, despite the fact that f is a constant, in one context, its partial derivatives are typically not 0. Returning to our example, x to the fourth plus x squared y squared plus 4x minus y to the fourth power equals 1, dy dx is negative f sub x over f sub y. Looking at the formula for f and thinking of the x and y as being independent variables, the derivative with respect to x is 4x cubed plus 2x times y squared plus 4, because we're treating the y in this context as being a constant. Meanwhile, the partial of f with respect to y within this same context is 0 plus x squared times 2y, 2x squared y. 4x has no y in it, minus the partial derivative of y to the fourth power with respect to y is 4 times y cubed. By rearranging our equation until it says some expression involving x and y equals a constant, and using the chain rule, we have therefore been able to get a formula for the slope of the tangent line in terms of the x and y coordinates of points on the graph. Hopefully this is easy enough for everyone to clearly understand. I'll talk to you again soon.